Welcome to Exponent Land. This is 6.1 Exponent Properties, and there are quite a few of them. So, number one is the product of powers. And what that states is if we have 3 to the second power times 3 to the third power, that would be, and how we can think of it mathematically is, well, there's two threes times each other, and then we have three more threes multiplied together, which is a total of 3 to the fifth power. And so our product of powers for algebra states that if we have a base A and we're multiplying those together, if we have to the power of m and the power of n, then we can just keep the same base and add our exponents. And that's that power of powers. Now skip a little space here because we'll come back to that in a second. And we're going to do the quotient of powers, which is very similar to the powers, product of powers. So it's if we have a base of 7 to the fifth over the same base to the third power, that would be, well, we can think of it as 5 sevens in the numerator multiplied together and 3 sevens multiplied together in the denominator. And we can see that these sevens, 3 of them cancel each other out to make a 1. Do you see how it makes a 1 for each one of those slashes? And we're left with 7 as our base, and there are 2 of them, so our exponent is 2. So the rule here is the rule for quotient of powers is if we have the same base and we have our exponents m and n, then we have the base number m minus m because we subtract 5 minus 3 to get 2. Now that 2, this gets a little complicated when, say, they were switched, like the bigger numbers on the bottom. So what I like to do is I think this part right here is kind of, the middle part is thinking exponents. So when we're in exponent land, we're thinking exponents. So like over here, we thought about how many 3s we had here first, and then we added 3 more 3s. Well, we didn't add them, we multiplied them, but we added the exponents. And so same thing with that simplifying, you can think in your head exponents. You have 5 sevens up on the top, 3 sevens in the bottom. 3 of those 7s will cancel out. I'm left with 2 7s multiplied together, and they are on the top. The leftovers are on the numerator, and that's where this one is in that numerator. Now, when we continue on with this, we have to think to ourselves, well, when do we multiply out? Because I know you're thinking, well, 7 to the second power is 49. Yeah, so this one we should write it as 49, unless unless it says to, well, even then when it says to write it as positive exponents, you always want to simplify what you can. And what that is your multiplication table. And a little more. Now, this is not a specific math rule, but I've noticed in a lot of the problems in different textbooks and in different videos and stuff, most mathematicians will simplify what they can for exponents. Now, when we get to variables, you won't. You would just leave them as positive exponents. But for, say, 7 to the second power, we know that that's our multiplication table of 7 times 7. Now let's take a look at 3 to the fifth. Now some people think, well, I don't know what 3 to the fifth is. Well, here's what we do is I like to use my finger. So for exponents, it's really nice to use because usually they're in the 5 to 10 range, somewhere in there. So we have, right now I'm using all 5 fingers on one hand, and they're represented by the 3. If I was over in the quotient one, I would use them as 7s, but for this one I was using, number 1, I'll use them as 3s. So I have 5 of them, so I kind of group them together. 3 times 3, I'll put 2 together to make 9, and then another 2 to make 9, and then I can put those 9 times 9, that's 81, and I still have an extra thumb, which is a times 3, so 81 times 3. So 81 times 3 is a little bit more. We had our first 3 times 3 is 9, or not 9, or 9 times 9 is our multiplication table, but then one more is just a little bit more. So that would be 3 in the ones place. 3 times 8 is 24. So 243 is our number, and we should write that out as a little bit more number. Number 4, example number 4 is, what do we deal with? How do we deal with negative numbers? So negative 2 to the second power, does that equal negative 2 to the second power? So what exponents do? Exponents affect exactly what is in front of it. So this 2 affects the negative 2, because the negative 2 is in the parentheses. It will have 2 of them. So that would be negative 2 times negative 2 is a positive 4. Bring down my question mark. Is it equal? So now if I look at the other side of the equal sign, this 2 affects what is directly in front of it, which is the 2. So the 2 is what is multiplied by itself. So the 2 and the 2 is what the exponent of 2 affects. So 2 times 2 is 4. And, I have a negative, so I'll bring it down. So are they equal? No, they are not equal. So I will put a slash to that, saying that they are not equal. So it looks very similar, but this one has the left side has a parentheses, and the right side, well, the parentheses is only around the 2. Example number 5. Now we get into the interesting ones. So what is 2 to the 0 power? Well, some people call it 0. Some people call it undefined. Some people call it 1. Some people call it 2. So here's what we do is we make a table of our exponents and our standard numbers. So when and this is a good way to help if you ever forget 0 or even negative exponents, you can build yourself a table. So we'll start with 2 to the third power, 2 to the second, 2 to the first, and then we'll go down to 2 to the 0. So I like to start at 2 to the first because that's 2. 2 to the second is 4, 8, and the next one's 16. So as we're going up, we're multiplying by 2. And why we multiply by 2 is because we see as the exponents go up 1, we're increasing it by a times 2. So there's one more times 2. And that's what exponents means. So now if we take and look at going the other direction, what if we go backwards? So if we go from 8 to 4, that is a lot of people think of it as divide by 2, but we're going to multiply by the reciprocal. And in exponents, it's actually really helpful if you start to do it that way. Instead of thinking it as division, it's always multiplying by that fraction. It just makes everything so much easier. So that means if we're going to go down 1 exponent, minus 1 exponent, we're going to multiply by a half. Multiply by a half. So if I go down 1 more to 0, we're going to multiply by a half. And 2 times 1/2 is 1. So the exponent of 2 to the 0 power is 1 as our solution. Now, will that happen to all problems? Well, we can kind of think of another, let's do 3's. 3, 3, 3 to the second, 3 to the first, 3 to the 0. And when we kind of go down, we're going to multiply by that 1/3. So at 3, we'll multiply by 1/3. Oh, it will be. So anything to the 0 power will always be 1. So any number to the 0 power equals 1. Or you could say any number negative 2.47 y to the 43rd all to the 0 power equals 1. Because that whole thing, no matter what's in that parentheses, is to that 0 power, it equals 1. Now let's take a look at what goes down in the negative exponents. So what happens when we get to negative 2 to the negative 1 power, 2 to the negative 2 power, 2 to the negative 3 power? So we continue our multiplier of 1/2, or some people thinking in their head, divide by 2, which is okay. But we'll want 1 times 1/2 is 1/2. 1/2 times 1/2 would be 1/4. Or, well, let's use, since we're in exponent land, let's use 1 over 2 to the second power. And 2 to the negative 3 would be another times 1/2, so that would be 1 over 2 to the third power. So if we take a look at what happens to our exponent when it's negative, so if we have 2 over 2 to the negative third power over 1, or we can put it over 1 to make it a fraction. To make it a positive exponent here, we can move it from the numerator down to the denominator. And that changes. So if we take a look at this 2 to the negative 1 power, if we kind of, okay, it's a negative exponent, so I want to make it a positive exponent to really understand it. I'll put it in the denominator. So that means it's 1 over 2 to the first power, a positive number exponent. So let's take a look at an example of that just with a base number of 4. So 4 to the negative 3 power. All right, so if we have 4 to the negative 3 power, it's really complicated to think what that negative does, even for me. So this is my kind of, I take and circle what that negative exponent affects. So like up here, if this 2 was the parentheses, I would circle that whole parentheses up here. But that 4 is what's being affected by that negative 3. I want to make it a positive exponent, so I will put it into that denominator. And when I rewrite it, it will have a positive exponent. So that negative 3 becomes a positive 3. And now I have kind of a filler here. I need a filler up here, so that will be a 1. It's kind of a placeholder sort of thing. So now the question is that part of my multiplication table? So I'll start with 3 fingers that are 4 each. I'll think of them as 4s. 4 times 4 is 16, and 16 times 4, that would be 64, because I could break the 4 into 16 times 2, and 32 times 2 is 64. So that is part of my multiplication table and a little bit more. So I would simplify it down. All right, example number 5. Now we get, that was 4. We get into more examples. 1 over 3 to the negative 2 power. So now our negative exponent is in the denominator, so to make it positive, we will take that exponent with its base, what's right in front of it, and move it to the top to make it a positive exponent. So don't get caught with that to change that negative to a negative 3. The exponent does not do any of that, and it's over 1 because we can leave a filler there. So 3 to the second power is just 9. Example number 6. If we have negative 1 to the power of 251. So I'm thinking in my head, exponent thinking. I'm thinking I have ones. I'll have 251 of those times itself. Well, they're always one. Now I'm thinking of all these negatives. So I'm going to think of a group of them, just to kind of to start thinking about how I'm just going to throw some down. And I'm going to think, okay, so a negative times a negative is a positive. So I'm thinking I'm going to group them into pairs because each one of these will be a positive, a positive. Oh, so if I had 6, my end result would be a positive. If I had one more negative, an odd number, then I would have a negative. But if I had another negative, so make it an even number, then those two would become a positive. So I have 251. So 250 of them would all be positives because they pair them up and you have 175. And one more would be a negative. So our end result would be -1 in its simplest form. Number 7. Now, I need a little bit more space for this one. So if we have x to the -2 power, y to the 0 power, over x to the 4th power times y to the -3 power. So now to simplify this, I notice I have a couple of interesting things. This one right here will simplify to 1 because it's anything to the 0 power is 1. This -2 power, notice how I circled the base number with the x, will move down into the denominator to become a positive exponent. This x to the 4th will stay. This -3 power, y to the -3 power, will move to the numerator and the exponent will become positive. So when I go across, I kind of march across the top, especially when there's more of them, and I just kind of put them in the right places. So the x to the 2nd goes in the denominator where I wanted it. We have a times 1 up here. Now I'm down in the denominator. X to the 4th stays in the denominator, and y to the 3rd power in the numerator. Now, from this step, I don't want to do too many steps in one and kind of add them and move them at the same time, because that's where a lot of the errors in thinking in your head happen. So for me, I like to show my one step of moving and then do that simplifying of x to the 6th power, y to the 3rd power in the numerator, and then we're simplified. Now, the 3 and the 6 do not cancel out because remember, if we think in exponents, there's 3 y's times each on the numerator, so that would be a y, 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 all multiplied together. And we have 6 x's down here, all multiplied together, but none of them cancel out. Okay, so it's not the exponents, it's the base numbers that we have to think about.